is like the problem is we are just given two files, suppose x and y, and the size of the files are, suppose its size is 5. 5 means length, numbers of element in that particular file, 5 and 10. So when we simply, or we can say the length of these files are 5 or 10. When simply we simply merge them, these two files, and a new file will be created, that is JAD. So the total number of moves mean total number of operation in the comparison, like in the merging process. So that will be 15, means we will have a new file of the size 15. So it is not I think a critical task here when we are having only two files. Like we can merge x with y or y with x. It doesn't affect. But let's suppose we are having more than one file, and if we are having more than one file, then let's suppose we are having x, y, z. So it may be possible like we can merge x and y, and the resultant, just suppose it is m, that will be merged with z, or we can merge y and z, and the resultant, suppose that is n, that will be merged with the x. So the sequence can be different, and this is the sequence for these three files. But if suppose we are having uh, several files, a very long list of files, then the process and between the merging process, we can select any particular file. So the point is here, the merging, simply merge the file so that the total number of moves, or we can say comparison operations, can be reduced. Okay, so in this optimal merge pattern, we simply apply an approach that is known as the greedy approach. So I am just we can just understand it with this particular example here. Suppose we are having two files, like suppose x1, x2, or a third file x3, and the length of the first file is 30, x2 20, and x3 10. And let's suppose I am just taking these two files first, 30 and 20. And if I will simply merge them, then it will be, there will be 50 moves, and the third file, sorry, the merged file will contain 50 elements. The length of the merged file will be 50. Now just merge this file with this third file, that is 10. So it will cost around 60. The total number of moves will be 60 plus 50, that is 110. So these are the number of moves. Like if we are just merging first 30 and 20, then merging the resultant with the 10. Now let's suppose we are just merging these two first, x2 and x3. So if we simply merge them, then there will be total 30 moves, means we will have a new file with 30 elements, or the length 30, and then we can merge this one with this 30. So we will have move 60. So total moves will be 60 plus 30, that is 90. So you can see here, when we are just merging x1 with x2 and then merging resultant with 10, then the total moves are 110. And when we are merging x2 and x3 and merging the resultant with the first file, then the total number of moves are 90. So you can see here this second option is having minimum number of moves. So the problem is we are given n number of files, and we need to merge all the files in a way that the number of moves will be minimum. So how that can be possible? So we apply the greedy approach here, like in every stage while we are just selecting the files to merge, which files we need to select to merge. Like you can see here, the size of this 30 and 20, it is largest one, the smallest one, and it is merged with this one. And in this case, these are two smallest one, 20 and 10, then these are merged, and after that it will merge with the largest one. So it can be possible, like in the every intermediate stage when we are selecting two files for merging, we can select the two least files which are present in that situation. So every time we will select two least files and we simply merge them, a new file will be created, and we simply put that new file in the appropriate position in the particular list. Okay, so that's the greedy strategy which can be utilized here in the optimal merge pattern. Okay, here are some important points here. So the merge pattern will be referred, it can be referred as a two-way merge pattern, because in each step we are having two files for the merging process. So this two-way merge pattern can be represented by a binary merge tree. Binary merge tree, like suppose we are having one file like this, another file like this, and length of this file is 5 and its file 10, then we will get a new file of size 15. So other important thing is this, like we are representing this the result in the form of a tree, that is the binary merge tree. It is binary means it is having only two children nodes. So what is important in this, you can people can see, like the original files are denoted by the squares. This is the original file, this one is the original file, and these are denoted by the squares. And this file, this is the merged file which we get after the merging process. It is represented by the square. So the original files that are represented by the squares are known as the external files, and the merged files which are represented by the squares are known as the internal files. Okay. So each internal node has exactly two children, and it represents the file obtained by merging the files, represented by two children. Okay, so the number of node, so number in each node is the length of that particular file, mean number of record in that particular file. Okay, so leaf nodes, that is the original files which are drawn as squares and represent the given files, and these nodes are known as the external nodes. And the remaining nodes which are drawn in the form of circular form, then these are known as the internal nodes, जो कि जो merging process के बाद हमको मिलेंगे, those will be the internal nodes. ठीक है. So now first of all, what is the binary merge tree? So ये मैंने बता दिया last slide में. A binary merge tree with external nodes representing entities and internal nodes representing the merge of these entities, merges of these entities, then this kind of structure is known as the binary merge tree. What is the optimal binary merge tree here? So basically, like in the merge procedure or during the merging process, we can select any one file for merging. So there can be several combinations for the merging process, or we can get several different binary merge tree. But which one will be the optimum one? So the optimum one will be like whose root is having the minimum value, mean that represent basically the total number of moves. So in the case of optimal merge tree, like we are just finding the optimal solution. So it is a kind of optimization problem. Means for this merging process, we can have several different binary merge tree, or we can have several feasible solutions. But out of these those several feasible solutions, we need to find out the optimum one. Okay. So the sum of paths from root to external nodes is optimal. That is the minimum one. Here the optimization is minimization. So assuming that node I contribute to the cost Pi, it means the length of that particular, no, it is not the cost here. It is the path length from the root node. And the path from root to such node has length Li. एक मिनट रुको. Okay, so this one is the length Li. It is the length from the root node to that particular node, and Pi is the cost of that particular file, or the length of that particular file. So what we need to find out after representing all the files in the form of we can say the binary merge tree, we need to find out the external weighted path length, that is the total number of moves. Like we are having a file here, it is 2, it is 3, and it is 4. So 2 plus 3 5, and 5 plus 4 9. So in this process we are selecting two least files, then merging them, and again selecting two least files and merging them. Now we need to find out the total number of moves or the external weighted path length. So that will be cost of that file, means for this 2 into cost of that file, mean number of edges from the root to that particular node. So this external weighted path length will be calculated for the ordinal files only. Ordinal file means which are denoted by the squares. So for 2, the external weighted path length will be like 1 here, 2. So 2 into 2 plus, for 3 it will be 1 2, again 3 into 2 plus, for 1 it is 1, so 4 into 1. So it is 2 into 2 4, plus 6 plus 4, that is 14. Okay, so this is the value of this actional weighted path length. So just we need to minimize this. And how can we simply minimize it? In every stage we will select a node, select the files having the least cost or the least value. Okay, so this is the algorithm for the optimal merge pattern here. मैं पहले आपको ऐसा करता हूँ, इसका एक एग्जांपल एक्सप्लेन करता हूँ, and after that we will go for the algorithm, because after that it will be easy for you to understand it, and then we will go for the complexity analysis. Okay, so the optimal merge pattern, let's suppose we are given a set of files like this. Now we need to arrange these elements in the ascending order. अब इनको हम ascending order में arrange करेंगे. Why we are arranging them in the ascending order? Because every time we will select two smallest files from the list. So in the list, like in the first iteration, we will select 2 and the 3, that is the minimum element to merge. Okay, so here is the list in the sorted form from left to right. Now we need to follow the steps. So insert 2 and 3, or simply merge 2 and 3. So you can see here 2 and 3 is here and are denoted by the squares. And after the merging process, we will represent that in the form of circle. Means the value will be 2 plus 3 5. Okay, as it is the sorted one, so after this process, these will be deleted from here. So we'll get the list like this: 5, 7, 9, and 13. So this 5 can be here. We are having a tie here, so it can be put here or here. Okay, let's suppose we are putting it here. Now in the particular list, which files are the having least cost, that is 5 and 5 again. So we'll merge this. So just see here, this 5 is represented by the circle because it is we have created it after the merging process. This is the original file, so this will be represented by the square. And after merging, we will get a node whose value will be 10. Okay, so it is removed from here, it is removed from here. So we are having a list like this: 7, 9, 13. And new file that is of size 10. So we'll put this file here. Then 7 or 9 will be merged. It will be 9 plus 7 16. तो मैं इनको हटा देता हूँ यहाँ से 16 and 9 और 7. 10 और 13 it will be 23. So ये 23 हो जाएगा और ये हमारे को यहाँ मिल जाएगा इधर 23. एक तरफ आ जाएगा 13 और एक तरफ आ जाएगा ये पूरा ट्री. Now we'll merge both of them and we will get a tree of 16 plus 23, that is 39. Okay, so this will be the whole process. Now Megbar can understand, explain you by this by these slides. Initially we are picking 2 and 3 and we will have a tree like this: 2 plus 3 5. Then 5 and 5 will be selected, then 5 and 5, it's 10. 10 will come here. Acha, then 7 and 9 will be selected. So in this slide, like 7 and 9, it is 16. Acha, 7 and 9 के बाद क्या आएगा? 10 and 13. So this is 10 and 13. Now we're having two trees like this: 16 and 23, rooted at 16 and 23, and simply merge them. So we'll get a tree like this. So this is the optimal binary merge tree. And why it is optimal? Because we have applied here the greedy approach. How? We are selecting every time when we are selecting two files for the merging process, then we are selecting the files with the least cost. Okay, so now we'll find out the actional weighted path lengths or the number of moves which are required in this merging process. So total कितने number of moves थे? जैसे हमने initially I have explained to you in some slide, like if we are merging 3 files, then number of moves are like this. So it will be we will calculate actional weighted path length. That is the profit, or we can say cost of, sorry, not profit, cost of this particular node multiplied by the path length. Okay, so the cost of this particular node, it is 7 and path length is 1, 2. So it will be 7, it is here 7 multiplied by 2. For this one, 9 multiplied by 2. For this one, sorry, this one 9 multiplied by 2. For this one, 2 multiplied by 1, 2, 3, 4. 4. ऐसे इसके लिए 1, 2, 3, 4. 3 multiplied by 4. इसके 5 के लिए 1 2 3 5 मल्टीप्लाई बाय 3 और 13 के लिए 13 मल्टीप्लाई बाय 2. Okay, so this is the after just solving this we will get 93. So 93 is basically the total number of move. तो ये हम verify भी कर सकते हैं. We can simply sum up the cost of the sum of the value of the nodes represented in the form of circle, because वो हमारे merging process में हमको achieve हुई थी. So it is like 5 plus 10 है ना, then plus 16 plus 23 plus 39, that will be also equal to 93. So this is the minimum one. Okay. I hope the process is clear to you all, like how we are just merging them. जैसे हम Huffman coding में कर रहे थे, selecting every time 2 characters with the least frequency, and here we are selecting every time 2 files with the least cost. और जब उनको merge कर देते हैं तो हम क्या करते हैं, लास्ट में उनको place कर देते हैं original list में. ठीक है. So algorithm देखते हैं इसका एक algorithm है. So this is the algorithm. This is the least L. Means we need to find a tree in L whose root has the smallest weight. L is the list. So हमको वो optimal binary search tree find out करना है using that particular list. This is a function we are passing here, that list and n. These are some variables. So we'll run a loop here from I equal 1 to n minus 1, because every time means for every iteration we will select 2 least cost node or the files and simply merge them files. And after merging them, what we will do, we simply place them in the appropriate position in the list. तो ये n minus 1 टाइम एग्जीक्यूट हो रहा है, ये n टाइम एग्जीक्यूट नहीं हो रहा, बिकॉज लास्ट में हमारे पास एक ही फाइल बचेगी. ओके, सो एवरी टाइम और इट विल बी एग्जीक्यूटेड. सो व्हाट वी विल डू, वी सिंपली क्रिएट अ नोड. हम एक नया नोड क्रिएट करेंगे, जैसे हमने नया नोड क्रिएट किया. अच्छा, अब इसका लेफ्ट चाइल्ड चाहिए, राइट चाइल्ड चाहिए. सो विल फाइंड आउट द first smallest element or the file from there, and we will put that here, the left child, and the second one it will be at the right child. Right child typical list of L, the second smallest element. Acha, what is the weight of this? So weight of this is 5 or 3, so weight of this will be weight of left child plus weight of right child, it will be 8. And after merging process we simply insert this into the L. So this T will be inserted into the L, तो इसकी appropriate position पे insert हो जाएगा. So this process will be repeated again and again, means up to n minus 1 time. And after this loop will terminate, so we'll return that particular least cost tree. Means we will have a single tree or tree rooted, means having the root with the minimum value. So this is the whole process. So now let's understand what can be the complexity of this particular optimal merge pattern. So you can see here this process is running around O of n minus 1 times. Now when it will execute n minus 1 times, so the complexity of this process will be constant O of 1. Complexity of this process and this process means we are just finding the smallest element. So इसमें हम क्या करेंगे, कंपैरिजन करेंगे. लेट्स सपोज वी आर अप्लाइंग द we can say the selection sort here, then it will cost around O of n. ठीक है, अब उस पर भी नहीं जाते हम, तो हम इसको इस तरह शो करते हैं. The finding of that particular element, so it is the finding of the smallest element. अब ये क्यों किया हमने ऐसा, क्योंकि we can have several different cases. Now we are talking about the अच्छा, this one will also cost constant value O of 1, क्योंकि यहाँ पे केवल summation operation कर रहे हैं. And this one inserting that particular newly merged node into the list, so it will cost. So we can write it like inserting. The complexity will be O of n minus 1 plus O of finding plus O of inserting. अच्छा, ये तो n minus 1 होगा. No, not plus n minus 1 multiply by, क्योंकि ये इसके अंदर है, this is the outer loop, and these two processes are inside this particular loop. अब इनमें से जिसकी ज़्यादा कॉस्ट होगी, मीन्स एलिमेंट फाइंड करने की या उसको इंसर्ट करने की, that will be multiplied with the O of n minus 1. So here the complexity will be like T equal O of n minus 1 multiplied by max of O find minimum, comma O of cost of for insertion in the list type. ठीक है. So this can be the time complexity. Now we will analyze it in different cases. Like in the case 1, suppose the list is not sorted. तो अगर जो हमको इनिशियली हमने क्या किया, जैसे हमने तो जो सॉल्व किया था उसमें लिस्ट को सॉर्ट किया था, और सपोज हम लिस्ट को सॉर्ट नहीं करते हैं, तो उस केस में what will be the complexity for this and what will be the cost for this. So find a minimum, that is O of n. So we can use first to pass for selection sort, and that will give us the minimum element. So in the case of selection sort, what is the process? Selecting the minimum element and place that at the first position in the list. So that will cost around 2n time or O of n time. Okay, and after that जब हम उसको merge कर देंगे, that then cost of insertion will be required. तो जब ये sorted ही नहीं है तो हम क्या करेंगे? We'll place that newly created node in the last of the array. So that will cost around theta of O of 1 time, क्योंकि उसको आपको बस array में last में place करना है. So ये outer loop हो गया, ये अंदर इसके loop हो गया, contribution हुआ और इसका cost है O of 1. So total कितना हो गया? O of n minus 1, या इसको हम n ही assume करके चलें. So O of n multiplied by O of n, that is O of n square. So this is the case when the list is not in the sorted order. Okay, now suppose the case 2, the list is just in the sorted form. And again we can have two cases, like how we are simply implementing that. So the case, suppose the case 1 2.1, like finding the minimum. अब अगर वो sorted form में है तो जो first two elements हैं वो ही minimum होंगे, so it will take constant time. सेकेंड वन इज द कॉस्ट ऑफ इंसर्शन, मीन्स उस पर जिनको मर्ज कर देंगे तो जो नया लिस्ट बनेगा उसको हमको इंसर्ट करना है, तो ये सॉर्टेड है तो हमको ढूंढना पड़ेगा कहाँ पे इंसर्ट करना है. तो दे विल बी एन नंबर ऑफ कंपैरिजंस ओवर देयर, सो इट विल कॉस्ट ओ ऑफ एन. नाउ द आउटर लूप इज हैविंग ओ ऑफ एन माइनस 1 एंड इसके अंदर ओ ऑफ एन एग्जीक्यूशन हो रहे हैं, तो इट विल कॉस्ट अराउंड ओ ऑफ एन स्क्वायर. सो इन दिस केस ऑल्सो द कॉस्ट विल बी ओ ऑफ एन स्क्वायर. So we, as it is a tree basically, and we can simply, rather than storing in a simple array on any other place, we can simply store them in a min heap, because every time we need the minimum value, so the L can be represented as a min heap, and value in the root is the less than or equal to the value in the different child. We have studied in the priority queues the heaps. So over there we have discussed the process of different processes on the max heap. Okay, so I think you people know the difference about them, the max heap and min heap. In the case of max heap, the root node contains the highest value. In case the min heap, the root node contains the minimum value. हमको यहाँ पे क्या logic, हमको क्या चाहिए यहाँ पे? We need the minimum value every time. Okay, so we will represent the L using the min heap. So if we are representing in the form of min heap, then suppose we want to find out the minimum element, then it will cost to O of log n time. अब वो log n time कैसे हो रहा है, थोड़ा सा रिकॉल करो. मैक्स हीप में क्या था, क्या प्रोसेस था? मैक्स हीप में जो भी हमारे पास नोड हुआ करते थे, हम क्या करते थे, व्हेन वी वांट टू एक्सट्रैक्ट दैट पर्टिकुलर मैक्सिमम वैल्यू, इसको हम यहाँ से रिमूव करते थे और रिप्लेस किससे करते थे? लास्ट एलिमेंट से. मिनी वाले केस में भी ऐसे ही होगा, इसको हटा देंगे यहाँ से, उसको रिप्लेस करेंगे इससे, फिर होगा यहाँ पे जैसे वहाँ पे मैक्स ep5 प्रोसीजर था, यहाँ पे होगा मिन ep5 प्रोसीजर. तो दैट विल कॉस्ट अराउंड टाइम O ऑफ लॉग n. एक बार स्लाइड्स आप रेफर करना, ठीक है. नाउ व्हाट इज द कॉस्ट ऑफ द इंसर्शन इन L? इंसर्शन ऑपरेशन था मैक्स हीप में, उसमें हम क्या करते थे, उसको लास्ट नोड में यहाँ पे इंसर्ट कर देते थे और फिर उसके रूट नोड से कंपेयर करते जाते थे और उसको जो भी उसकी अपडेट पोजीशन थी वहाँ प्लेस करते थे. एंड इन द वर्स्ट केस दिस प्रोसेस विल टेक ऑफ लॉग एन टाइम. व्हाई? बिकॉज it will compare it with the parent, then swap parent, and up to the height of the tree. The height of the tree can be a log n. So there will be total log n comparison. So find minimum में भी log n का contribution हो रहा है, and cost for insertion इसमें भी log n का contribution हो रहा है, and this is bounded with the outer loop, which is suppose executing n time. So the total cost will be n log n time, n log n, that is n log n. So this is the complexity. So if we simply representing the particular list using the min heap, then the complexity can be reduced and it will be O of n log n time. So hope it is clear to all.